Good morning, and thanks for this opportunity to present our work, Millimeter Wave Signal Technologies for Digitizing Biodiversity. So why monitor pollinators differently? So we all are aware that importance of pollinators, and we should monitor them using sustainable and non-invasive, cost-effective methods. And visual method has been always the foundational for biodiversity monitoring, especially for identifying and classifying insects. So imagine we have additional layer of information that could capture the biomechanics of the insects, such as its wing flapping patterns and how it reflects certain frequency that camera quite can't see, even the human eyes can't see. So there lies this millimeter wave signal technology. So the millimeter wave signals that comes in the range of 30 gigahertz to 300 gigahertz. So this wavelength is more comparable to many of the insect size. So it's more sensitive to its motion and its behavior. And it could be used in all weather and day and night, and it's non-contact. So in order to identify and classify the insect, here we exploit the micro-Doppler effect due to the wing flapping. So you might all aware about the Doppler effect. So if a target is moving, then the reflected signal will be having some frequency shift compared to the transmitted signal because of its translation motion. If the target has some additional motion, such as its wing flapping, it will cause some micro-Doppler effect. And this wing flapping pattern could be different for different insect types, and maybe it would be species specific. And this wing flapping patterns could act as the biological fingerprints. So this micro-Doppler patterns could be used for identify and classify the insect. So for that, in order to capture that, in experiments, we kept the insects near to the millimeter wave antenna and captured the reflected signals from the insect wing flapping. So the first figure that shows a power spectrum comparison of different scenarios when insect is not present, when present, and the insect flapping its wings. Because of the periodic motions of the wing flapping, there is harmonic peaks in the power spectrum. And in the spectrogram, the first 7 seconds, insect is flapping its wings. And there are some patterns at the first 7 seconds. And we conducted these experiments on different types of insects. And this includes wasp, honeybee, and different types of bumblebees. We could see that in the spectrogram, this wing flapping pattern induced micro-Doppler effects are different for different categories. So we collected more data from these types of insects, and we employed advanced signal processing algorithms to extract the relevant features that represents different species, and employed a classification framework so that it can classify the data into different taxonomical levels like family, genus, and species. And for the collected data of 5 different species, we could be able to achieve an 85% of accuracy. So this is shows some feasibility that we could use some non-invasive, compact, scalable methods to identify the different species in an area. But also we could identify the behavioral data, like what all species visiting the floral site, and the frequency of flower visit, and what all insect that dominate under different environmental conditions. So this could be used as a complementary approach along with the current digitizing biodiversity monitoring methods. Thank you.
Thank you very much.